So my name is Flavio Dell'Acqua and I'm a senior lecturer at King's College London. I'm working for the Department Forensic and Neurodevelopmental Sciences, but also I've been working with the neuroimaging department. My main research is advanced diffusion imaging methods and how we can apply them to study stroke, neurosurgical planning and psychiatric disorder, even for development like autism, for example. So I can show you some of the slides and so give you a general overview of what we are doing here and also why we are doing this kind of research. So as you know, diffusion, probably when we talk about diffusion, we talk about diffusion tensor imaging, and diffusion tensor is kind of a spatial imaging technique, different than any other methods, because we are not just taking picture of the brain, but we actually measure how water moves inside the brain. So we have almost a vectorial three-dimensional information how water molecules move inside the brain, and because of this we can actually see how fibers and microstructure is organized. So for the first time we can actually have directionality. We can see where fibers are going in different parts of the brain. So with DTI, with very relatively simple tractography algorithm, we can follow this trajectory and we can use some mathematical tools to reconstruct different trajectory, and we can see that what we obtain with DTI tractography match quite nicely what we can see with post-mortem dissection. Of course, with different rules, we need to kind of tweak the algorithm, but overall we can get a very nice result. And just to give an example, if we can compare what we can do with normal DTI tractography, we can reconstruct the major white matter tract like projection system, commissura, associative tract. And these tracks, in a way, are what we were able to see in the past to post-mortem dissection. So before we had to open a brain and say, look inside. Now we can do exactly the same thing with diffusion MRI. Now this is really powerful technique, but can also give us a different insight, not just to look at the brain like that, but we can also do some study. So first of all, we can look how different brains are different between each other. For example, we know that some subjects are more left lateralized, some tract, other tract are more bilateral, and by looking at this intersubject variability, we can actually characterize different populations. But clearly, the main application we have today in tractography is neurosurgical planning. So we can definitely help neurosurgeons and neurologists to define where, for example, tumors are expanded, how they're expanded, and design different way of approaching the surgery. And again, this is something we are pushing in our lab, is probably using anatomy as a way to predict recovery. So if we know, for example, that some tracts are affected, but there is some kind of another tract on the side of the brain that can compensate for the missing, we can have a chance of recovery. So this is something we are really interested to use tractography to look at anatomy using anatomy as a way to predict recovery, like for example in this case was a patient.
When you talk about the lateralization and looking at the arcuate fasciculars, can you combine that with functional MRI data in the way that fMRI is quite often used for language lateralization to help?
Yeah, definitely. I mean, there are some studies that compare the two methods like fMRI and DTI, and they can provide and definitely DTI can provide complementary information, because while fMRI sometimes is related to more the activation, here is more related to the actually underlying microstructure. So you might have the tract, but if they are not there, you don't do the task correctly, or you don't think something a certain way, the task is not showing up, right? So here is telling you what are the road, the function is telling you who is right, if the road has been used or not, in a way. Okay, so this is a general idea of what we're doing with DTI, but clearly DTI is only part of the story. We know that when we look, for example, at some tract, we know something is missing, what we call false negative or false positive. So we see tract that should not be there, or some tracts are missing, or sometimes if you look at a FA, you can see region here like black holes here, but this is not a lesion, this is a healthy brain. Why is that? Because in a way, DTI, what it's showing us is always an average of what's going on in each voxel. So we have these kind of smarty fields in a way that tell us how diffusion is organized, but we can only see a very general and approximate trajectory of it. So we can see something about the corpus callosum here, corticospinal tract, but not much. So what we really want, we want to look at more in detail what we don't see here. So but many people were asking, do we really need advanced models? So how bad is it? Well, we did different study, and we show, for example, that if we map, for example, the number of crossing across the brain, different studies show that at least between 70 and 90% of the brain areas show crossing fibers. So using a single fiber model like the TTI, you can only see a single fiber orientation. You can actually missing quite a lot. So this is an atlas we created by averaging different subjects. You can actually see where there are 2 or 3 fibers, essentially, except the corticospinal tract here and the corpus callosum. Everywhere else you have crossing. So you see, it's really important to take into account these methods. So how we do that, there are clearly different approaches, and the community is really active on looking at different ways of solving crossing, but everything is based on orientation distribution function, ODF. And essentially, these are kind of, instead of representing diffusion like an ellipsoid, you represent everything like this kind of spherical function where the peaks tell you where the fibers are in different directions. And for example, in the case of diffusion orientation distribution function, or diffusion ODF, what you have, they are very blurry shape. They actually try to represent displacement of water molecules. So they are quite blurred because they actually follow the diffusion of water. Then there is another family of application called that essentially spherical deconvolution is based on. They generate the fiber orientation distribution function, or FODF. And here what they're giving you is a much sharper profile, because they are not giving you the displacement of water molecule, but they're trying to recover the underlying fiber orientation. Okay? So, and that's where in our lab we are focusing on. So we're working a lot on spherical deconvolution method. And if you look at the same data set we have shown before here, now if you look at the what you can see with spherical deconvolution, now you can start to see a lot more information. You can see now the crossing of the corpus callosum with the corticospinal tract. You can see U-shaped fiber in the cingulate region. So a lot more information. So the main thing is we are not seeing only the dominant fiber orientation, but also secondary, tertiary component. And if you have this information, it's quite easy to then apply this to tractography, and then now you have this new reconstruction. Now you can see it is on the left, you have the diffusion tensor. You can actually see the normal representation. Now you can say you see more fiber, you can actually see much better reconstruction. And if you compare here, you have just 60 diffusion direction, BU 1500, 3000, which is close to what people normally do clinically for a DTI. It's a little bit more, but not so much more complicated. So I think everyone should be able to run this type of acquisition.
And I notice it says cardiac gated. What's the impact of trying to take out some of that physiological?
Well, this is something because when we do research, we want to be very reproducible. We want to make sure that across acquisition we are able to get always the same result. And cardiac gating is helping in this direction. Of course, it's also making the scanner a little bit slower because you have to pause the scanner to wait to avoid the systolic peak only to and you want in the diastolic phase. But I would say most of the applications with tractography today are done without considering cardiac gating. It's not a big deal. We are just doing it because we are quite picky. We want to get the best quality.
Because you can.
we can, exactly. Okay, so one thing I want to mention is that there are different methods to do spherical deconvolution. And what we did in our lab, it was to look at not the general case when you have only healthy fiber, simple crossing. What we were really interested in is to look at what's happened, for example, when you have partial volume with gray matter, or also contamination with the edema, like in pathological tissue. And what we found out that most of the methods always kind of are in trouble when they have a contamination in their signal, when there is a signal of the white matter plus something else. So what we did with the temperature solution, we're trying to develop a particular regularization. Actually, it can take care of this contamination and still give you quite reliable fiber orientation estimation. That's kind of a unique feature of the temperature solution algorithm. So with this information, so this was a simulation, but you can also see here in vivo data, you can see, for example, normal spherical deconvolution give you some kind of spurious peaks very easily near the gray matter, and when you have the visualization, everything gets smooth, but at the same time you preserve the ability to resolve crossing in the deep white matter. So when they tissue is fine, spherical deconvolution is great, but when you get closer to gray matter, CSF, or lesion, you want to make sure that you can rely on the fiber estimate. Otherwise, you get a lot of random track, and there will be a problem. So when we've done this, then the next step really was to look at tractography. And one of the first study we did was actually to look at some tracks that were not visible before with DTI. And for example, we published with Michel Thibault de Schotten in Nature Neuroscience. Was the first time we were able to see the 3-segment OSLF. We were described only on the monkey before. And we're able to see that with just a 10-15 minute acquisition and using spherical deconvolution. After that, we start to look not just at big track, also smaller track, for example, U-shaped fiber or intralobal track, because with spherical deconvolution now you can see, not, as I said before, not the main component, but also the secondary component, the subcomponent of in the white matter. So you still see smaller track, and here you can actually see what we call the poppy flower. It's a sort of a set of U-shaped fiber around the hand region, connecting the premotor, sensory area, and motor area, all connected. It's a kind of a nice network of connection that we think coordinate the fine motor tuning. Okay. So in our lab, normally we have this kind of approach. So we always try to study normal anatomy first, and then we look at disorder. And in fact, we kind of learn how to dissect different track of this kind of new track we can say with spherical convolution, and then we apply to different disorder or pathology. For example, here we apply SLF and visual spatial attention with Parlantini, for example, ADHD, on stroke in the case of neglect. Then we also have primary progressive aphasia from the frontal tract, and also, of course, looking at neurosurgical application or the brain stimulation application. So we understand how to do the track, and now we can apply.
So for these kind of applications, are you looking more qualitatively at the tracks once you're able to visualize them with your algorithm, or do you then move even further to something more quantitative, and that's where you see the difference?
Clearly, well, first of all, you want to see if there is a track, because you want to see what is visible. And of course, then you want the quantification. So when you have a quantification, you can start looking at a normal volume, or you can look at also at kind of some matrix. And while with DTI, you normally look at normal voxel-wise matrix. One of the things you can do with spherical deconvolution is also to look at what we call track-specific matrix. So for example, if you look here, and you can see that if you have a pathological track crossing with a healthy track, you can clearly see that with spherical deconvolution is able to detect changes on a specific bundle or fiber or track, while the other one is healthy, is not changing. In comparison, if you look to DTI, you can see that there are some changes, but mostly in the orientation of the ellipsoid, and also if you look quantitatively, you see these are very small changes in comparison of the big changes completely disappear. All one track completely disappear, and the other case is just little. So we developed, and other people work on the similar idea. So we come up with this index called orientation isotropy. Other people call this apparent fiber density, and it's something that actually is really close to the underlying microstructure organization of the specific fiber. It can be an approximation of fiber density, but it can also be an approximation of the radial diffusivity of each bundle fiber. Okay, it's not just fiber; it is a mixture of those. So that's why we prefer to have a more general term. But pretty much is you can exchange the two terms fine. So if you do that, now where you can see, for example, you map this matrix, you can clearly see now the difference. So FA is going down in the presence of crossing because they have the tensor averaged out of the two fiber, and you lose an isotropy. On the contrary, if you look here, you can see the two different values are different for the different track. And now you can imagine to apply this for pathology. For example, you can imagine you have a healthy corticospinal tract crossing with the pathological arcuate. You can actually see strong high intensity of CST and low intensity of the arcuate. If you look at the FA, it's just the average. You don't see the pathology if it's there. And some studies already start to come out using this matrix to, for example, this is a group in collaboration with Leuven, and they're able to see that this matrix is more specific to detect changes, for example, related to language and reading. So that was an example. Now we have a study under review on looking at neurosurgical planning and TMS stimulation. So also there is a strong correlation between this metric and these electrophysiological measurements. So now this what we are doing here is mostly for research, and if I think about more than 10 years now, in 2008 when I started in this institute, to do spherical convolution was about, we need to collect data for 20-25 minutes. It was quite slow. Now with new scanner is 30 minutes, but clearly if you really want to deploy to the clinical community, you really need to have data that can be acquired much faster. And luckily now now we have moved from single shot, single band acquisition. Now we have multiband, and we can collect multiple slides per shot with API. And now you can see the time is go down from 30 minutes to 4 minutes and a half. Now with 4 minutes and a half, I think that everything we have been done for the last 10 years in research can be clearly applied to all in every clinical population. So essentially, we are ready to deploy this for clinician.
Okay. Do you see any compromise when you're using multiband in terms of, I don't know, data quality or any other issues that people should be aware of?
I think that overall the quality of multiband data is pretty good. There is I would say there is some penalty, but a very minor penalty in SNR. But overall, the time gain you have, for example, instead of collecting 60 direction in 4 minutes and a half, you can collect 90 direction in 6 minutes, and you're still much better than 12 minutes or with the older generation. So there is a clear advantage in using this data. So, okay, just to finish, I want to show you that sometimes people say that we do pretty picture. It's true, we do pretty picture. And this, for example, we won an award with this picture. It's true there are pretty picture, but we can also use the same picture to do validation. That is an important thing. So you can see this is a study we did in collaboration with Marco Catani. We actually see using this kind of tractography, way of visualization we call digital degerring. You can actually see in the post-mortem dissection that we can see the same structure, the right structure. So frontal tract, U-shaped fiber are there. So there is a lot of reproducibility. So clearly photography is not perfect. There are some problems, but what we are seeing is, in a way, is a reflection of the underlying anatomy. So we are getting closer and closer every day with this.
So with these kind of new techniques, we can obviously see more with MRI than we've been able to see before. So then is there an opportunity to use MR images a lot more for education?
Oh yes, that is actually what we want to do. We organize workshop in our lab, and we try also to organize way to disseminate this information. For example, one thing we are doing at the moment is working on an atlas, actually based on the same images. And the idea is to teach anatomy, and at the same time guide the clinician to understand, for example, why there are some symptom related to some particular lesion in the near the cortex in region where normally with normal tractography just show white matter, but doesn't show any obvious track. So now we have this kind of work in progress, but we're getting there. We have more than 150 tracks then based both on DTI and spherical deconvolution, and we can actually now cover most of the white matter. Before, if you look at the best tractography algorithm available, if you overlap all the tracks, you can cover no more than 50% of the white matter. Right. Now we are getting there to cover most of it. So essentially now we are starting to guess much better how the brain is connected.
Okay, that's fascinating. Thanks very much.
Okay.